So welcome to the video lecture on data communications. So today we'll be discussing about wireless LAN's protocol IEEE 802.11. So as we discussed in the last session, so IEEE 802.11 is part of the IEEE 802 set of LAN protocols. It is defined for the different LAN protocols. 802 is basically defined for wired LAN, wireless LAN, and also the other wireless technologies like Bluetooth. So all are defined under 802. So here for wireless LAN, the particular LAN protocol name is IEEE 802.11. So what it does, it specifies the set of media access and physical layer protocols. So that is nothing but the data link layer protocols and physical layer protocols for implementing the wireless LAN in the various frequency bands like 2.4 gigahertz, 5 gigahertz, 60 gigahertz, like that. So these are the different frequency bands which we will discuss later. So what is IEEE? As you all know, IEEE is Institute of Electrical and Electronic Engineers. It's an organization. So IEEE standard subdivided the data link layers into two sublayers. Okay, that is logical link control and media access control. The two sublayers of data link layer are logical link control and media access control that we already discussed in the previous session. So now we'll be particularly talking about wireless LANs here. So the architecture of wireless LAN defines two kinds of services. Okay. There are two kinds of services. The first one is basic service set. In short, we call it as BSS, or extended service set, ESS. So BSS, you can see here in the diagram, BSS is a basic building block of wireless LANs. So it is a standalone or an ad hoc network. Ad hoc network, we can see here, the stations form the networks themselves. They join together and themselves form the network. That form is called ad hoc network. So they don't need any basic infrastructure like access point or any other infrastructure. They form the network themselves and point anywhere. Okay. So what is there in BSS? So BSS is made up of stationary and or mobile wireless stations. So these stations can be either stationary, like our computer, okay, computer or a router it can be, or they can be the movable, like our mobile phone. Okay. And optional central base station. So and central base station can be there or it need not be there. That is called the access point. Access point is not mandatory here. So the first one is called ad hoc network, that is without AP, without access point or the central base station, is called the BSS without AP or ad hoc network. Here in diagram you can see the first one. The second one is similar to the first one, but you have an extra station that is the central base station, or in other words it is called as an access point. Okay, that is called infrastructure network. So this is called infrastructure network here. So now the second one here is extended service set, ESS. You can see in the diagram here, it is made up of 2 or more basic service sets. Okay, basic service sets with APs here. That is mandatory here. AP BSS with AP, because AP here is connected to the distributed system here. You can see there are, in the diagram, there are 3 BSS with AP. Okay, all the APs are connected to the distributed system here. So that distributed system may be a wired LAN. Okay, wired LAN. Okay. So you can see in some of the organization, like our organization, where wireless LAN is connected to the wired LAN. So there are access points. So you can connect your laptop or mobile to the access point. The access point is connected to the wired network in our or the college it is. So that is the best example of that. This one, ESS. The distributed system connects APs in BSS as mentioned here. So ESS uses 2 types of stations. Again, ESS can have mobile or stationary. So here AP, all these stations can be either mobile or stationary. Okay. So the mobile stations are normal stations inside a BSS. So they are all normal stations inside one BSS. So we say that stationary stations like APs are stationary stations that are part of wired LAN. You can see all these are stationary. APs are stationary stations. They are connected to this distributed system, where distributed system is a part of the wired LAN. We have different types of stations. So station types in 802.11. 802.11 defines 3 types of stations. So based on their mobility in the wireless LAN. The first one is no transition mobility station. It is a station, it is either a stationary or moving only inside a BSS. So no transition is either stationary or it's a stationary station, or it may be a mobile station, but only within that BSS. The second one is called BSS transition mobility. So it can move from one BSS to another BSS, like here. You can see this. From one BSS to another BSS, it can move from here to here. So that is called BSS transition. But the movement is confined inside one ESS. As you can see here, there are 3 BSS. This station can move to the second one or third one, but they should be within one ESS. The third one is ESS transition mobility. So it is a station, it can move from one ESS to another one. One ESS to another one. Again, if it moves from one ESS to another ESS, you'll have communication continuity problem here. However, here IEEE 802.11 does not guarantee the communication is continuous during the move, because there will be switchover from one AP to another AP. That is basically called the handover from one to another one. So this basic protocol like 802.11 does not guarantee this the continuity here. So there are different other protocols uses for this. So that is beyond the scope of our discussion here. Now you have frame format. As you know, the data link layer. Now we are talking now the data link layer. What we call the logical link control, LLC layer and MAC layer. There are 2 layers of data link layer, 2 sublayers of data link layer. So we are talking about the frame format. As we know, data link layer is responsible for framing the payload which is received from network layer. So this is the frame format of IEEE 802.11 or wireless LAN. You see here the frame format has, this is the frame body. Okay, frame body is this. It will be either 0 bytes or maximum number of bytes will be 2312 bytes. Okay, so this frame body is nothing but the payload received from the upper layer. When I say upper layer, it is network layer. Okay, so data link layer giving the service to the upper layer. Okay, so that payload contains the original data, that is information, as well as the headers added in the upper layers. So when we talk about that, we call it as this is a payload received from the immediate upper layer, that is network layer. So it can be 0 bytes or 2312 bytes. What is the meaning of 0 byte? That means this will be 0 bytes. That means it will have only the header. All these are headers here. All the remaining fields, including this, are header and trailer. This is trailer. Okay. So there are some frames where we don't have the payload received from the upper layer. The frames created here itself, they are called the control frames or management frames. We'll discuss there later. Okay, they don't have frame body here. Okay, so here you can see now. Let us discuss these the fields one by one. You can see FC, frame control. It's a 2 bytes long. Okay, 2 bytes here, 16 bits. So that FC frame control has subfields. You can see 2 bits, 2 bits, 4 bits, and remaining all are 1 bit. Let us talk about this. What are these fields? The frame control, FC, it's a 2 byte long, 16 bits. The first field here, version, see this protocol version, it is 2 bits are for that. Currently, current version is 00 here. So currently the version is 00. Later it may be modified. If it is modified later, it will change. Okay, right now it is 0. Its value is 0. Both the bits will be 00. And type, it is type of information. That is, as I said earlier, there are 3 types of frames here. Okay, either the data frame or control frame or management frame. Okay, data frame will have payload received from the upper layers, where these two will not have any payload received from the upper layer. So they are basically the frames created in the there itself without the data part or the frame body. So in order to differentiate these 3 frames, so here this field is used. So 00, 01, 10. If it is 00, it is management frame. If it is 01, it is control frame. It is 10, then it is so data frame. If it is 11, so it is undefined. It's an invalid frame. Then subtype, there is 4 bits for that subtype. So subtype, we'll see that later. Subtype. Then here you have another 2 more bits. We'll see this later. There are two DS and from DS. So this bit will be either 1 or 0. Their meaning we'll see a little later in the next slides. Then address 1. Similarly here, more flag. Here it will be there. So more flag. So more flag is when it is set to 1 means more fragments. So that means here the frame is again divided into fragments, small data units. Okay. For the first fragment, it is 1. For the second, third also it is 1. For the last fragment, this particular flag will be 0, saying that no more fragments will be there. That is the last fragment. For all the remaining fragments, it is 1, set to 1, indicating that more fragments to receive. Okay, those fragments need to be rejoined at the receiver side in order to make the complete frame. Then retry, as we told earlier, if it is a retransmitted frame, it is 1. If it is a first time transmission, it is 0. So retransmission may occur in the flow and error control method that we discussed earlier. The power management, when it is set to 1, means station is in power management mode. So in the wireless LAN or any wireless networks, the power management is the very important issue here, because all the stationary are operating using ordinary power, cell power. So if it is in the power management mode, then it is set to 1, otherwise it is 0. So it is basically sent at the sender side. Then more data, when set to 1 means station has more data to send. So when a station has some more frames to send, then it is set to 1. Then here it is related to the encryption. That is, if an encryption is for security purpose, if an encryption is implemented in the data link layer, then it is used. Then reserved, this last bit is reserved, it is not yet used, it is. So may be used in future. Similarly, we have a D here, D flag, you can see this, D or ID it is called, D or ID. So this D or ID in the all frames, it defines the duration of the transmission that is used to set the value of network allocation vector, so NAV. So there is a value of network allocation vector. It is basically defines the duration of the transmission. In the data frame and management frame, it is that. When in control frame, this field defines the ID of the frame. Okay, only in a control frame, it is the ID. Whereas we have 1, 2, 3, 4 addresses. Okay, all are 6 bytes. Say these are all MAC addresses. There are 4 MAC addresses. Okay, so 6 bytes. Why? Because MAC address is 6 bytes length. We have already discussed earlier. 6 bytes long. It is generally defined using hexadecimal colon notation. So why there are 4 addresses? That also we'll discuss little later in the next slide. Okay. Then SC, sequence control. So it defines the sequence number of the frame to be used in the flow control. As I have discussed earlier in the flow control, stop and wait protocol. We discussed stop and wait protocol. So in stop and wait protocol, every frame, it can be either stop and wait protocol or its advanced versions are there next protocols, automatic repeat request. So it will be either 0, 1 bit or more than 1 bit are used to specify the sequence number of the frame. So every frame will have a sequence number. It is used for flow control. And frame body, as I said, it is varies from 0 to 2312. This is the payload received from the upper layer. And frame sequence, that is frame checking sequence, 4 bytes. Okay. So this is, you can see here, this is a CRC32 error detection sequence. CRC32 error detection sequence. Here, CRC32, this is CRC32 error detection sequence is used. 32-bit here, 32-bit. As you have seen earlier in the cyclic redundancy code. So we form the code word. How do you form the code word? The code word is now formed using you have a data word and you have a generator code word, generator polynomial. Using generator polynomial or divisor, we divide the data word. So this particular FCS contains the generator polynomial which is used here. Then all these remaining we discussed. Now, what is the total number size, the maximum size and minimum size of this frame? You can see the minimum size. You can see minimum size when frame body is 0. 0 bytes. Maximum size when the frame body is maximum. Okay, that is 2312 bytes. So you can see there are fixed, all these are fixed. So 2 plus 2, 4, plus 6, 10, 16, 22, okay, 24, 30, 34 bytes are fixed. So 34 plus 0 is equal to 34 byte is a minimum length of this 802.11 frame. Similarly, 34 plus 2312. 34 plus 2312, it is 2346 is the maximum, okay, length of the IEEE 802.11 frame. It is. Okay. Next up. Here, as I said, we have 3 types of frames: data frames, management frames, and control frames. Data frames are used for carrying data and controlling information. So it is carrying data, and sometimes they also use controlling information, like as I said, sequence number, error checking, all are control information. So they carry the data as well as this. Okay. So this particular data frame has the payload received from the upper layer, whereas management frame is used for the initial communication between the stations and access points. So there will be initial communication. Some handshake signals are exchanged before they actually transmit the frame, data frame. Initially, whether a station is ready to send, or it is engaged, or an intent acknowledgement will come from the other side. So like that, there are some management frames are exchanged between the stations. So such frame is called management frame. Similarly, we have control frames. Control frames are used for accessing the channel and acknowledging the frames. So this is used for accessing the channel itself. Okay, because more than one, as you've seen in the previous discussion, more than one stations will be using the same channel. Who has the right or the access is decided by the protocols earlier we discussed. So that is basically getting the control of that channel is done using control frames. And similarly, after sending the data frame, at the end of the data frame, that is after receiving the frame, the receiver will send the acknowledgement to the sender. So that is called acknowledgement frame. So acknowledgement frame is also a control frame. Okay. So therefore, we have 3 types of frames in 802.11 standard. As I said, see, in our previous slide, I told this, what is the meaning of this? Okay, these two. Here, to DS and from DS. Again, the subtypes, that is subtype of this these frames. Okay, in the management frame also we have different subtypes, and even in the control frame we have different subtypes, so different frames. Again, to differentiate those subframes, these subtypes are used. Okay, then to DS and from DS, both are one bit here. Carefully see this, both are 1 bit. Their meaning we'll see now here. Now, this particular table, you can see, along with the address field. You may ask why there are 4 addresses here. Only sender and receiver is sufficient, right? One address for the sender, another one for the receiver. Why we have 2 more fields here? So they are required because it passes from one BSS to another BSS, from station to access point, from access point to another station it may go, or it may pass from the frame will pass from station to access point, from one access point to another access point, from another access point to a station. Okay, or it will be received by an access point will receive a frame from the station, like that. Okay, there are different types of communications here. Okay, So those communications are differentiated here by these two bits, to DS and from DS. D stands for destination and S stands for source. Okay. So here add 4 addresses, you can see here. IEEE 802 addressing mechanism specify 4 cases here. Now, how the 4 cases depends on the bits here, 00, 01, 10, 11. The 4 cases are there. So, accordingly, the interpretation of 4 addresses in the frame will change. Of course, every address field is 6 bytes long, but their interpretation is different here. Okay, interpretation. Now let us see what is this. The first case. Okay, 00. Now 00. See here, if 00, both to DS and from DS, both are 00 here. Case 1, let us talk about this. Case 1. Carefully listen and see this diagram. Both are 00 here. To DS is 0, from DS is also 00. Now, address 1 is a destination address. Address 2 is source. You can see here in the table. Address 3 is BSS ID. Address 4 not applicable here. Okay. Now, in this case, you see, what type of communication it is? You can see a frame is sent from one station to another station within a BSS without the use of AP. AP is not used here. This station is directly sending to this station, station B. Okay. Now, see here, there are 4 addresses. The meaning of 4 addresses, 1, 2, 3, 4. As you see in the table, 4th address is not applicable here. Address 3 is a BSS ID. This one, the ID of the BSS. The BSS itself has the ID address here, the MAC address. So that is here specified in the address field 3. Address field 2 has source address. Which is source here? Source is A. So therefore, this field has the source address. Similarly, the address field 1 has destination address. Which is destination address? So destination is B here. So the MAC address of station B is specified here. Okay. So in other words, when to DS is 0, from DS is 0, a frame is not going from distribution system to another distribution system. You can see here, not going to a distribution system, or it is not coming from another distribution system. Okay. Okay. Here DS is not so destination source. Of course, sorry. It is DS stands for distribution system. Okay. There is a correction here. D stands for distribution. S stands for system. So 2DS is 0, meaning that frame is not going to a distribution system. And again, the second bit is also 0 because frame is not coming from distribution system. That means where a frame is going from one station in BSS to another station without passing through the distribution system, that is within the BSS address. Okay. So this is the case number 1. Now, case 2. Here, case 2. Here you can see this 2DS is 0, from DS is 1. You can, by looking in this here itself, you can say 2DS is 0, from DS is 1. That means it is not going to distribution system because it is 0. From DS is 1. So therefore, that means it is coming from distribution system. You can see here. It is coming from a distribution system, from another BSS. So how it will come? It is coming from an access point here. So a frame is received from access point or coming from access point and going into a station. Which is the station here? It is B in our diagram. Now let us see the address field. See the address field again. Address field 4, not applicable. This one, not applicable. Address field 3 is source. Which is source here? Access point. Sorry, not access point. It is A. So it is coming from station A in another BSS through the distribution system. So therefore, source is A. So therefore, the address field 3 has the address of A here. Then address field 2 will have the address of sending AP. Which is sending AP? This is sending AP. So address field 3 will have the address of sending AP. Then address field 1 is a destination. Which is destination? Station B is a destination. So therefore, address field 1 has the address of the station B here. Okay. So this is about this case number 2. Now the reverse of this, case number 3. See here. 2DS is 1. What is the meaning of 2DS? Frame is going to another BSS through the distribution system. You can see our diagram. The frame is going from this station, this is the source, to this B is the destination through the distribution system. Frame from DS is 0. So that means it is not coming from another distribution. So it is going. So that is why the second bit is 0. And the frame is going from a station, this is from station to AP in the distribution system. Now let us see this third case. Again, address field 4 is not applicable here. This is not applicable. So this is blank here or invalid here. Of course, not invalid. It is a don't care values here. Then address 3 field is destination. Which is destination here? Destination is B, station B in another BSS. So this field has the address of station B. Address field 2 is source. Which is source? A. So A, the address of A is here. Similarly, receiving AP. Address field 1 is receiving AP. So which is receiving AP? This is the AP. So its address, that is AP. This AP's address, MAC address is there in address field 1. Okay. So this is about case 3. Now, case 4, both bits are 1. You can hear 2DS. That means a frame is going from one distribution system to another distribution and it is coming from another distribution system. Okay, here from A to B through this AP and this AP here. Okay, in this case is not passing through the AP here. You can see this AP, this B is within the coverage of this AP also. So therefore, it is going here. It will go like this here. Okay, you can clearly. Here it is another way. One AP to another, from AP it is going because this is not within this part of this. Okay, not the coverage of this. That is why it is 2 APs are used. So that's why both bits are 1. Now this is source, A is source, B is destination. Okay. Now address field 4, source address. Which is source? A. So this is A now. The address A is in address field 4. Address field 3 is the destination address. Which is destination here? Station B. So therefore address field 3 has the address of station B. Then sending AP, address 2 has sending AP address. So which is sending AP? AP1 here. AP1. So its address is here. And similarly, receiving AP is AP2. Its address is in address field 1. So like that, these 2 bits will differentiate the 4 cases. Okay, 4 cases and 4 different scenarios or 4 different types of communications in our extended service set, or it may be BSS also. Okay, it may be BSS because the first case is BSS here. Okay, first case is BSS without AP here. Okay, so this is about the frame. Okay, structure of wireless LAN IEEE 802.11. Now there are some problems here. Okay, there are 2 cases we'll discuss. There are 2 problems. Problems in the sense in the transmission, problem in the transmission here. Now you can see this is station B. This particular first problem what we're discussing is hidden and exposed station problems. Okay, hidden and exposed. First we'll discuss the hidden station. What is hidden station? Let us see now. Here, see there's a diagram here. This diagram, this one, this particular is the range of B. The second one is the range of oval shape. First oval shape is the range of B. Second oval shape is the range of C. It is. Okay. So every station in this can hear station B, whereas every station in this range can hear station C. Here in the sense it can send or receive. Station C is outside the transmission range of B. Here you can see station C is outside the transmission range of B. It is. Okay, only A is within that, within the range of B. Station A, however, is in the area covered both B and C. So here station A is within the range of B as well as C here. Okay. Now, okay. See here, what is this problem? Let us see. Now assume that station B is sending data to station A. Station B is sending data to station A. This B is sending to A. Okay, B is sending to A. So in the middle of the transmission, station C also has the data to send. Now in the middle of the transmission, what happened? C also has some data to send. To whom? To A only, it is again. Okay, C also has the data to send to A. So this transmission is going on. In the middle, C wants to send data to A now. Okay. However, C is out of B's range here. Okay. Now you can see C is out of B's range. It is not knowing that B is sending the data to A. Okay. So outside the range, and transmission from B cannot reach C. Therefore, C thinks the medium is free. It thinks that the medium is free because C cannot hear B here. C cannot hear B. Okay. Now, what happens? Station C sends its data to A. C will send to A. Okay. What is the result? This will send to A. Result is there is a collision because there is already a transmission is going on between B and A. So there will be a collision here. Okay. Collision at A because this station is receiving data from both B and C. So in this case, we say that station B and C are hidden from each other with respect to A. Now, station B and C are hidden with respect to A. Okay. So C is hidden to B, whereas B is hidden to C with respect to A. So there will be a collision here. So how to solve that problem? Okay, this can be solved here. How it is seen, this diagram here. Now, the solution to hidden station problem is the use of handshake frames. As I said, handshake frames, that are called management frames. Okay, what is this RTS? Request to send. Okay, request to send, RTS frame. So, CTS means it is clear to send. Okay, clear to send. CTS means clear to send. So here, you see here, the RTS message RTS message from B reaches A now. Initially what happens is request to send message control information, it is goes from B to A. So here now the medium is free, so therefore B will send this control frame again. Management frame, that is clear to send to B. Okay, but clear to send to B. Whereas this RTS will not reach C. It goes only A because C is outside the range of B here. Okay. Now, because both B and C are within the range of A, see here, CTS is sent by A. This is A here. A. Both B as well as C will receive this CTS message. Now what happens? C will come to know that somebody is using the channel. How it will come to know that? It is receiving CTS message here. By seeing this CTS message, it will not send the data. Why it will not send the data? Because it has not sent the RTS message. Okay. And so therefore, by seeing this CTS message, C will think that somebody else is using. Who is somebody else here? In our case, it is B. Is using the medium. So therefore, I will not send the message. Okay, I will not send my data frame. So therefore, it will stop. So this is how this particular collision problem or the hidden station problem can be solved. Station C knows that some hidden station is using the channel and refrain from transmitting until the duration is over. So station C thinks that the hidden station, which is hidden station, B is the hidden station, is using the channel and it will refrain from transmitting until that duration is completed. Okay. So this is how the hidden station problem is solved. Now, exposed station, how this is solved here, see. So in this case, now even though a station can send the data, but it is stopped. It is stopped or refrained from using the channel, even though the channel is available here. Okay, even though the channel is available. You can see here, there are three OLs here. This is as usual B. This one is C's range, whereas the middle one is A's range. And B and C both are within the range of A. Within the range of A. Whereas C is not in the range of B. Similarly, B is not in the range of C. Okay. And A and B are within the range of C. Now, let us see the scenario here. Station A is transmitting to station B. Now, A is, as usual, it is transmitting to B here. Okay, A is transmitting to B. station C has some data now. Again, C has some data to send to station D. Now, C has some data to send it to D here. Okay, this transmission is going on, whereas C also has some data to send it to D here. Okay, to D. And this C here, this cannot be sent now. C cannot send it to D. Here, of course, there is no problem for sending, but it cannot send. Why it cannot send? So, C is exposed to transmission from A here. See, this transmission is already going on. C is exposed for that transmission also. Okay, so this transmission, because the entire range, C is also within the range of A, so therefore this is exposed for this transmission. So it hears what A is sending and thus refraining from sending. So since it thinks that somebody is using the channel, it is not knowing that only B is using. Though it can send a message to D, it cannot send because this is exposed. This A is exposed to C, thinking that C will think that somebody is using the channel. I cannot send my frame. I cannot send frame. Of course, you can, from the diagram you can see this can be transmitted. Okay, so that is called exposed station. Which is exposed here? Which is exposed here? C is exposed to A. So therefore, transmission from C to other stations is stopped here. Okay, so it is, of course, the waste of capacity of the channel here. The channel is not used, cannot be used by other stations. So as you've seen earlier in multiplexing and all, this problem comes here. Okay, now even though we send that RTS, CTS control information, we cannot stop that. We cannot completely avoid that. You can see here, initially the handshaking messages RTS, CTS cannot help this scenario here. Station C hears the RTS from A. Okay, this is BACD now. Okay, BACD. A is sending RTS to B, this one. Okay, RTS message to B. Then that same thing goes to C also. You can see RTS message goes to B as well as C. Whereas B will send CTS, that is clear to send. Okay, and C will stop its transmission for some duration. Okay, some duration it is. And you can see here B, A got the clear message from B. It starts transmitting its data here in the yellow color. Okay, yellow color, and the same data goes to here also, see, to the C also. And this time duration, it will wait from here till here, it will wait. Okay, wait, but after that it will start sending an RTS message, request to send to A. But A is now sending data in yellow color, you can see, sending data. So there is a collision here. What is that collision? The RTS frame and data frame. There is a collision here. Okay. And again, of course, here it will go here. RTS message goes to D. Clear to send frame comes to here also again. Okay, there is a collision here also. Collision here as well as here. In both the places we have collision. Okay, so that cannot be completely avoided. Now the physical layer. It uses industrial scientific ISM band. The operating range you can see here, starting from 902 megahertz till 5.8 gigahertz frequency range. Different bands it can be used. is a frequency band. I mean the carrier frequency which is used for the transmission. And physical layer uses DSSS. What is this? Direct sequence spread spectrum, as we discussed earlier in previous chapters. DSSS is used. It's a spread spectrum here used is implemented here. How they are used? 11-chip Barker sequence, as we mentioned earlier. Either 1 or 2 Mbps data rate. Accordingly, the output of this will be 11 or 22 Mbps. And the modulation what we use is either BPSK or QPSK, binary phase shift keying or quadrature phase shift keying modulator is used. Okay, 11 megahertz analog signal is output of this. This is the implementation of physical layer. Of course, there are later there are some variations in IEEE. That is the variations or what we call the improvement. It is called 802.11a. It describes here all other remain same except to improve the data rate. In the physical layer, they have implemented this one, frequency division multiplexing, orthogonal frequency division multiplexing. As you know, the multiplexing or is the responsibility of physical layer. FDM, frequency division multiplexing, dividing the frequency band into subchannels, that we have already seen in the previous chapters. So there is this variation of orthogonal frequency division multiplexing, that is called orthogonal frequency division multiplexing or OFDM method. Okay, that is again to improve the bit rate. Okay, what is OFDM? See, all the subbands. As I said, the frequency band is divided into subbands. All the subbands are used by one source at a given time. One source they will use. The sources content one another at the data link layer for access. So all the sources will content one another for the media access. So OFDM uses PSK, phase shift keying, so or QAM, quadrature amplitude modulation. With PSK, the data rate achieved is 18 Mbps, and QAM with 54 Mbps is the data rate. So with OFDM multiplexing, PSK and QAM modulation techniques are used in 802.11a. Then we have 802.11b, one more variation. Here also DSSS is used, direct sequence spread spectrum is used. Then but one small change here, for encoding you have complementary code keying. A complementary code keying selector is used here. Complementary code keying, you can 5.5 or 11 Mbps the input. So before this one here in this place, this particular thing is used. Here, as you have seen earlier, QPSK requires two signals with the different phases. One signal goes like this, another signal goes like this. So this CCK, complementary code keying, will select this signal and this signal. Finally, the QPSK modulator will modulate this using this. Only again, this all these are same. Only this part, instead of BPSK, only QPSK is used, and we have in between some other thing here. That is again the one in the 802.11b. Then finally, the summary of all this different variation. 802.11 uses frequency hopping spread spectrum. It is operating in 2.4 gigahertz ISM band. So lower cost, low power consumption, most tolerant to signal interference, because most tolerant to other noise interferences. And 802.11 also uses DSSS in the physical layer. Again, it's operating in 2.4 gigahertz ISM band. It supports very high data rate, more range than the previous one here, frequency hopping or IR physical layers. Okay, what is IR? 802.11 infrared is there. Here again in the physical layer, we use infrared, lowest cost of compared to these two, lowest range compared to the first two methods. Range is lowest one. Does not penetrate walls, so no AWAS dropping here. Does not penetrate the walls from one room to another room. So because since the infrared is used, as you can see, infrared is used in our TV remote. You cannot operate your TV remote sitting in one room, keeping the TV in another room, because infrared has very high frequency compared to this one. So because they don't operate in 2.4 gigahertz, the frequency is very high, so therefore range is very small. Okay, and they cannot penetrate in the walls. Okay, similarly, IEEE 802.11a, as we discussed in the previous slide. So the data rate 6, 9, 12, 18, 12 up to 54 it is possible, and they use orthogonal frequency division multiplexing. Then 802.11, it operates in 2.4 gigahertz band, provides again very high data rates of 5.5 or 11 Mbps. It uses complementary code keying modulation scheme. And there is one more variation, 802.11g. 802.11g operates in 2.4 gigahertz band, provides data rate between 22 to 54 Mbps, and it uses orthogonal frequency division multiplexing. Okay, this is similar to the first one, A here. Okay, so this is about this one. So in summary, what we discussed in today's session is initially we have discussed the IEEE 802.11 architecture. There are two architectures, BSS and ESS. Okay, BSS is without distribution system, whereas ESS with the distribution system. And BSS we have access point or without access point. Without access point it is called ad hoc network, whereas with the access point it is called infrastructure network. And further it is extended, that is called with the distribution system, that is called ESS. Then we have discussed the frame structure and types of frames. There are 3 frames and different types of communications. Okay, then we have discussed the different implementation, the physical layer implementation of IEEE 802.11. Finally, there are different variations of IEEE 802.11. Okay, IEEE 802.11. Thank you all. Yeah, students, if you have any doubt, you can interact with me.